Alright, hello. So we are going to start with the third section of Chapter 9, looking at limiting reactants. So we're going to take all the information that we have learned from Section 1 and 2 with mole ratios and then incorporating mass, and now we're going to apply it to looking at all the reactants in an equation and determining which one might be limiting or controlling the reaction. Okay, so a stoichiometric mixture is a mixture that contains the relative amounts of reactants that matches the numbers in the balanced equation. So what this means is that all the reactants are completely used up. It's exactly with the mole ratio of the balanced equation. Nothing will be left over. It's like perfect, but we don't live in a perfect world, so this rarely happens. And so we have limiting reactants. And so limiting reactants are the one that runs out first. It limits the amount of product that can form. And so once it's gone, the reaction stops, and that's it. And so it's really important to determine which reactant is limiting because that controls the rest of your reaction and thus your calculations. Okay, so let's kind of do a quick review first. We want to find out what mass of water is required to react exactly with 249 grams of methane. Okay, well, first remember we want to balance. Let's see, I've got 1 carbon, I have 1, 2, 3, 4, 5, 6 hydrogen, so I put a 3 here, and it's balanced. I have 249 grams of methane. I want to know grams of water. Start with my 249 grams. So maybe if you want, you could pause this, do this on your own, and then just fast forward to the answer if you feel pretty comfortable with this stuff, and then you don't have to listen to me. Okay, so then we want molar mass of methane. Carbon is 12.01. And hydrogen is 1.008, and there are 4 of them, so we have 16.042 grams for 1 mole of CH4. Now that I'm in moles, I can use the mole ratio. Looks to me, with everything being balanced, that it's 1 to 1. So for every 1 mole of CH4, there is 1 mole of water. And then we need to go from moles to grams of water, so for every 1 mole of water, there are approximately 18 grams. Each hydrogen is about 1, oxygen 16. So if we calculate, we take our 249 divided by 16.042. 1 to 1, we don't need to do anything there, and then times 18. So we get 279.39 grams of water. If we stick with significant figures, it's just 279. Okay, so we know that 279 grams of water will react exactly with 249 grams of methane. That would be considered a stoichiometric mixture. Nothing's left over. Okay, so the reactants are mixed in stoichiometric quantities. But like we said, this isn't really practical. I mean, that's just never going to happen. So what if 300 grams of water reacted with 249 grams of methane? Well, now we need to know what's going to happen there. Well, since only 279 grams were required, if we react 300 grams, we're going to have some left over, or in excess. Okay, and so that means that our methane is the limiting reactant. It's going to run out. It's going to be used up first, and so it's going to control the reaction. Alright, so we must determine the limiting reactant to determine the correct amount of products produced. Okay, and so because that limiting reactant is going to control the reaction. Okay, so let's apply this in an example. So nitrogen gas can be prepared by passing gaseous ammonia over solid copper 2 oxide at high temperatures. So these are reactants. We know nitrogen gas is one of our products. The other products are solid copper and water vapor. So we want to know how many grams of nitrogen are formed when we have 18.1 grams of NH3 and 90.4 grams of copper 2 oxide. So we have information about both our reactants. That is a huge clue that this is a limiting reactant problem, because since we know information about both reactants, we've got to figure out which one's limiting. Okay, so the first thing we want to do is write and balance the equation for the reaction. So, I've got to go back. I don't remember what the reactants are. Okay, so copper 2 oxide and ammonia. Okay. So we have our copper 2 oxide. Well, the 2 means it's a 2 plus, oxygen's a 2 minus, so we're good there. We have ammonia. I know one of my reactants is the nitrogen gas, I believe. Water vapor. I can't remember the last one. Oh, let's see. Solid copper. Okay. Okay, and let's see. We've got 18.1 grams of NH3 and 90.4 grams of CuO. So 18.1 and what did we say? 90.4. And we want to know how much nitrogen gas, right? How many grams of N2 are formed? Okay. Okay, so we've got everything written. Let's see, we need our physical states. I'm guessing the ammonia. I think this is a solid. All right, so we've got it written. Now let's also balance it. So let's see. Copper looks okay to me. Oxygen looks okay. I've got 2 nitrogen, so it looks like I'm going to need a 2 on the ammonia. That makes 6 hydrogens, so I need a 3 on the water. Now we're changing our oxygens, so we want 3 oxygens over here. That changes our copper. Done. Now you could also use the math method or anything else to balance. Sometimes inspection is just faster, unless it gets really complicated. Okay, next. We need to convert our known masses of reactants to moles. Basically what we're going to do here is figure out, okay, what if copper 2 oxide was our limiting reactant and it produced some nitrogen gas? How much would it produce? And then we want to do the same thing with our ammonia gas and figure out how much nitrogen it produces and compare those and figure out which one's limiting. So let's take our, well, let's see what our next step is. Okay, I think we have room to do it right here. Okay, so let's take our, so again, this is what stuff we've already talked about. If you want to go ahead and convert the copper oxide to nitrogen gas and then just check your answer, please feel free to do that. It's good practice. Okay, so we have our grams of copper oxide. We know we need to get to moles first, so we're going to use molar mass. So let's see, copper is 63.55. And plus an oxygen, so we've got 79.54 grams of copper oxide. Then we're going to use our mole ratio. I can see that for every 3 moles of copper oxide, I've got 2 moles of NH3. Remember, I'm figuring out location because I want to make my units cancel out. And this should not be NH3. I'm trying to go to N2, so that's what I want. So I know for every 3 moles of copper oxide, there is 1 mole of N2. And, oh, let's just go to grams because that's what we want anyway. So let's see, nitrogen was 14 times 2 because it's N2, 28.02 grams. Alright, let's see if our copper oxide was limiting reactant, how much nitrogen gas we would produce. So 90.4 divided by, that's 79.54 divided by 3 times 28.02, and we get 10.62 grams of N2. So that's if copper oxide was limiting reactant. Now let's check our ammonia. So we're going to start with 18.1 grams of ammonia. Same idea, so we need molar mass first. So that's 17.034 grams for every 1 mole. And then we need to do mole ratio, so for every 2 moles of NH3, there is 1 mole of N2. And same thing, go to grams. We already did the molar mass, so I'll just take it from the top problem. Okay, let's calculate if ammonia was the limiting reactant, how much N2 would get produced. So 18.1 divided by 17.034 divided by 2 times 28.02, and I get 14.88. So just because we started with less does not mean that it's going to produce less. It's all about that mole ratio and molar masses, and it's, there's a lot of factors. Okay, so now let's take a look at both these. One of these will actually happen and one won't. Okay, so when copper oxide is completely used up, 10.62 grams of nitrogen gas are formed. When ammonia is completely used up, having excess of everything else, 14.88 grams of nitrogen gas are produced. Well, this one can never happen. because if the copper oxide produces less nitrogen gas when it's used up and everything else is in excess, then there's no way we're ever going to get to the 14.88 because the copper oxide is going to get used up before then. And so that makes copper oxide our limiting reactant, and that makes this quantity the grams of nitrogen that will be produced. And we need significant figures, and for some reason I just can never let it go, so 10.6 grams of N2 there. That's better. Okay, so you're comparing, you have to somehow take two different reactants and compare them on the same level. And so by converting them both to the product, we can see which one is going to produce less product, and that's our limiting reactant. So this 14.88 is never going to happen. Like, forget about it. It's not real because that copper oxide is going to be used up before we can even get past the 10.62. Okay, so we want to use those moles and the mole ratios and determine which reactant is limiting by comparing which reactant produces the least amount of product. So we just did that. It was the copper oxide because it produced less N2 gas. Okay, so the limiting reactant produces the actual amount of product. So that was our 10.6 grams of nitrogen gas. The other reactant then is in excess. And so since our ammonia is in excess, we could figure out how much is left over of that reactant. So let's see here. Let's go back. We had 90.4 grams of copper oxide, and we know that that was limiting. So if we wanted to find out how much ammonia was left over, we're going to start with our 90.4 grams of copper oxide. So this is our limiting reactant. This controls the reaction. We can use this to calculate anything else. So let's figure out if, since this is our limiting reactant and it gets used up completely, how much ammonia are we going to use up? So I forget the molar mass of the copper oxide, so 63.55. Okay, so 79. And it's the same type of calculation, because remember, we can use this mole ratio and molar masses to calculate anything in that reaction. Now we need the mole ratio, which of course I don't remember either. So for every 3 copper oxides, there's 2 ammonias. So for every 3 moles of copper 2 oxide, there's 2 ammonias. And, oh, that's moles. And then let's go to grams. So for every 1 mole of ammonia, what was it, about 17 grams? Okay, so let's calculate how much is used up. Times 2 divided by 3. Okay, so since we're using the copper 2 oxide as our limiting reactant, we can now go from grams of copper 2 oxide to grams of NH3. This is the number of grams of NH3 that was used up in the reaction. It's gone. It was reacted. Okay, and so now we need to take what we started with, which of course I don't remember that either, 18.1. Okay, and so we know that we started with 18.1 grams of ammonia. We used up 12.88 grams of ammonia, and now we can figure out how much is left. 18.1 minus 12.88. Okay, we're going to have 5.22 grams of ammonia in excess, or left over, or however you want to say it. Okay, so basically we haven't done anything new as far as calculations go. We're just taking the information and applying it to some, practical problems in chemistry. So we talked about limiting reactant, and then using that limiting reactant to, number 1, find the amount of product produced, and number 2, find out how much of the other reactant was used up so we could figure out how much was left over. Okay, so try some examples and practice problems, and if you have questions, let's go over it. Have a good day.